First off, I apologize. This video should have been part of the previous video, but I kind of cut off a little bit too short. But please check out the pH of buffer video before you watch this one for it to make any sense. So, determine the pH of a solution after 0.05 moles of sodium hydroxide is added to 0.5 liters of previous solution. In this case, the previous solution is my buffer that I created in this previous setup here whenever I was asking about the 0.2 molarity HA and the 0.3 molarity of the sodium A. And I went through all these steps, and again, check out the previous video. I kind of went through them much slower. But when we kind of talk about this one, I'm more interested now is after that buffer solution has already been created, I am now going to be adding some sodium hydroxide, which is a base, to 0.5 liters of this stuff, and I want to know the pH after this has happened. And so one thing we have to kind of note is buffers are made to kind of resist a change in the pH. I'm not saying that it's not going to change at all, it's just not going to change by a very drastic degree, as if you were just to add sodium hydroxide to straight HCl. And so in this case, I am telling you I am adding sodium hydroxide. So one thing you should be kind of fully aware by now is that sodium is going to break off. No one really cares about it. It's going to float around in water. The more interesting aspect we have to kind of explore is the concentration of hydroxide that is being added. And so here I give you moles, which whenever we start talking about concentrations, moles is only half of the information we need. The other half is the fact that I'm telling you that 0.05 moles of this hydroxide is being put into 0.5 liters of our buffer solution. And so the actual result of this is the amount of hydroxide that is being added is 0.05 moles over 0.5 liters, or 0.1 molarity hydroxide. And so the next step here is you should realize all we have now is a concentration of our hydroxide. But luckily for us, that previous solution, I gave you the concentrations of your HA as well as your conjugate base of A minus. And so now we are adding this hydroxide to that same solution. And so now we're no longer adding it to water. We are taking our hydroxide, again, from our sodium hydroxide, and we're adding it to the solution from before, which was composed of our acid and our conjugate base with water. And so here, we luckily know most of these values. From the previous question, I told you that the concentrations of the HA is 0.2. I told you the concentration of our A minus is 0.3. So we can plug those in as our initial concentrations because this is how the buffer was created using these two, again, the acid and the conjugate base. And so, additionally for this problem, we also know another factor comes in here to play, or the fact that 0.1 molarity of sodium or hydroxide is now being placed into this buffer solution. And so there we know that 0.1 is going to be the initial concentrations of our hydroxide. And so from there, we, again, luckily from Gen Chem, we know that all of our hydroxide that is inside of this sample now is going to react with this HA. And what happens when you have an HA plus OH? You create water. And so therefore, all of this OH minus is going to decompose. It's going to react with some of this HA. But in that same instance, whatever amount of OH minus is going to react with HA, it's going to produce water and A minus. And so here we know all of this hydroxide is going to decompose, or 0.1 is going to disappear. And if we know 0.1 of our hydroxide is going to go bye-bye, we also know that it's going to react with 0.1 of your HA in order to produce 0.1 of your A minus. And so here, just doing math, we have no x's. Our 0.2 minus 0.1 will give us a concentration at equilibrium of 0.1 HA. Because all the hydroxide ions reacted with some of that HA, we should have no hydroxide ions left over. Because we have 0.1 HA reacting with 0.1 of hydroxide reacting with 0.1 of our HA to produce 0.1 of our A minus, it goes from 0.3 to 0.4. So in this case, you should be asking yourself, why the heck did we even bother doing all that? The reason is because our new concentration or our new sample, once we add this hydroxide, has completely new values for our initial HA and our initial A minus. And so now we're actually looking at a completely different concentrations of our acid and our conjugate base. And so now we just have to write out a brand new rice table with our brand new equations and our brand new stuff kind of going on here. And so now again, if you compare this to all the previous rice tables, this is what we have seen repeatedly. But unfortunately, we didn't have this right off the bat because all of these values, which this was again 0.2 and that was 0.3, they change once you add this point or this hydroxide in there. But once we have our brand new relationship, our Ka is still going to be the same Ka now that we're looking at the acid plus the water to give us our hydronium ions plus our conjugate base. And so here we know that this is going to change by minus x. This is going to change by plus x. This is going to change by plus x because it's a 1-to-1-to-1 relationship. And then here, once we know this, our 0.1 minus x, we know this is our x. We know this is 0.4 plus x. And as I stated before, because we're looking at something that has the same Ka or Kb value from the previous, or Ka value from the previous one, then we know that we can plug in our 2.5 times 10 to the negative 5 for our Ka. X is going to be our hydronium concentration. 0.4 is going to be our concentration of our A minus because this X can be dropped off. And the same deal with your HA, you can drop off this minus X because, again, those changes are not going to be too dramatic when compared to that 0.1 and the 0.4. And I ran out of room on this side, so we're going to go up over here. And again, the X is equal to 6.3 times 10 to the negative 6, which is equal to the concentration of your hydronium ions. And since we're looking for pH, use that awesome equation, pH equals the negative log of your hydronium ions, or your pH equals negative log of 6.3 times 10 to the negative 6. It will give you a pH of 5.2. And so if you kind of compare this 5.2 to this previous question of 4.8, even though we added a strong base, it really did not throw off this pH by an extreme amount.